What's going on, everybody? Johnny Bannon here with Trepa Technologies, and in today's video we're jumping into automation and programmability in our CCNA course. So this video is a part of a series of videos of our free and full course on YouTube and our paid self-paced and live virtual training course on our website academy.trepatech.com. Hit that link in the description below if you want to enroll in our paid course with a bunch of features, practice questions, labs, and access to our team. Now with that sales pitch out of the way, let's go ahead and get started on today's video. So today we're going to jump right into automation and programmability by just doing a network automation overview. So we're going to go over what is network automation, why do we need it, and what are the overall high-level benefits of network automation. Then we're going to jump into the logical planes. So if you're watching our videos in order, you know that we've already gone over the control and data planes in section 1. We went over just overall fundamentals of networking. Now we're going to dive just a little bit deeper into those logical planes and get into the hardware components that function with those logical planes. And also one we didn't cover, the management plane. We got to understand these planes to understand how network automation came about and why we started doing network automation. And mainly when we talk about controller-based networking and the paradigm shift away from traditional and controller-based, you have to understand the logical planes and their roles and functions within the actual networking device and your networking architecture. Then we're going to get into the SDN or controller-based APIs, which are going to be southbound and northbound APIs. Of course, for some of you that may be watching this and saying, what about the REST APIs? We're going to get into that as well, not in this video, but we're going to talk about what an API is, the southbound and northbound APIs, and what they do in a software-defined network, and specifically a Cisco software-defined network. So we're going to use examples like DNA Center and SD-WAN to explain our southbound and northbound interfaces and APIs and what they do. Now, a northbound API just describes any API, or northbound and southbound APIs describes, if you look at the logical diagram, right? Southbound API interacts with the underlay fabric. Northbound API is anything external that lets you interact again with that fabric underlay, the actual data plane and southbound APIs. So the reason we don't talk about REST APIs in this video is because that is not just specific to networking. So we're going to have our own video on REST APIs and what they are in a general sense, and then go over what they do for networking. And then we're going to cap this video off with some whiteboard action where I'm going to compare automation to just controller-based networking. The difference is when you use one over the other, when you would combine, and why we go over the difference of automation versus controller-based networking, because it is a difference. Cisco has controller-based networking products like Cisco DNA Center, Cisco SD-WAN, Cisco Meraki, but that is not the same as automation. There's automation elements into those controller-based networks, and of course that's the whole purpose, having something central that allows us full programmability, looking at our network infrastructure not just as individual devices but as an entire, again, infrastructure. And then with network automation, that is more vendor neutral, meaning we can use technologies like Python and Ansible and Chef and Puppet to provision and do configuration management from a centralized device or server like an Ansible tower, but it's vendor neutral. And we can be a lot more specific in the task we want, and it allows us even more programmability in a vendor neutral environment. So we're going to go over those differences. Now, with that being said, let's go ahead and get started. Let me hide my face here and actually jump into the lecture. So as you can see here, network automation, that's the title of this slide. And then on our agenda, kind of what I already described, is we're going to go over just a quick overview of network automation, the planes, software-defined networking versus traditional. So we're going to go define traditional networking again, because even though that's what we've been learning this entire time besides our wireless section, we got to actually put it into a high-level overview of what we mean. We're going to go over APIs and what they are, and then we're going to go over the specific southbound and northbound interfaces when we're talking networking. Okay, so network automation overview. So task automation. So one of the many benefits is we get task automation with our network automation. So this includes device provisioning, configuration management, software updates, monitoring, troubleshooting, and security enforcement. So these are things, we're talking configuration, management, software updates, that traditionally we would spin up our secure CRT, our terminal emulator, go in and manually configure. But with network automation, now we can do this all at once and make it less error prone, take away the human error in that. And we'll go over what we mean by that. We also get efficiency and consistency. So by automating daily network tasks, organizations can significantly improve operational efficiency. Now, what do we mean by that? Now, imagine just something comes out, like a security compliance comes out that says, hey, all of our switches are now going to use extended range VLANs. So even a small enterprise, let's just say a small campus, that may be 20 to 30 access switches. And that's, again, a pretty small network for a network engineer to be working on. Typically, in a traditional network, how would we do this configuration? We'd have to go one by one and configure extended range VLANs, maybe 1,000 through 2,000. Well, again, there's maybe some human error, and automation ensures that the tasks are executed consistently and accurately. So that's a benefit. Now, obviously, if you're configuring 1,000 VLANs, that's a crazy network. Maybe you're in just the biggest data center in the world. And then we also have scalability. So network automation is essential for managing large and complex networks. So again, imagine you're working in an enterprise that has multiple campuses across the US or even internationally. So maybe one campus at minimum has 100 switches, not including the distribution and core layers. Well, how can you as a network engineer, the senior principal engineer, scale your ability to troubleshoot and manage and make configuration changes? Well, we can do that with network automation. Programmable infrastructure. So modern network devices, like your typical network infrastructure, routers, switches, firewalls. We say modern, think of like the Catalyst 9000 series of switches. That's the modern infrastructure we're talking about. Think of like CSR-based routers. They actually allow external systems to interact with and control them programmatically. So what do I mean by that? So with the use of APIs, which is a software interface, okay? So when we say the interface, don't think physical hardware. That's a software interface. On this Catalyst 9000 series switch, we are allowed, or we have that API available to us to allow an external device or app to programmatically configure us. So as an example, in Cisco DNA Center, Cisco SD-WAN, we have to onboard devices into that controller. Well, that controller uses APIs to interact with the actual infrastructure, that fabric underlay. How does it do that? With APIs. Well, what type of APIs? Well, southbound, when talking to the actual infrastructure, we use something called netconf and restconf. So in these modern devices, when it says modern network devices allow external systems, they're using these types of APIs to actually interact with that DNA center or whatever that single pane of glass controller is. We may have to configure that on the CLI and say, hey, enable netconf, okay? And then we have scripting orchestration. So over here, I have my NetMiko script. This is a Python script using the NetMiko library to automate a task and script out a task for a Cisco device. So as you can see here, network automation can be implemented through scripting languages like Python, also other ones like Ansible that we're going to talk about. And unfortunately, I have the most experience automating networks with Python, but it's not on the CCNA exam objectives. So that sucks. But Ansible I have experience with too, but we also have other ones like Chef and Puppet that we're going to talk about. Anyways, so I put this photo here because this is a good example of scripting orchestration. So we can provide that orchestration, and look at this one here. What we're doing essentially in this NetMiko script, let's say we got a task to create or onboard 20 new switches, and we don't have DNA Center. Maybe we're in a vendor neutral environment, but we decided to order 20 Cisco switches. So now we got tasked with automating some of the baseline configuration in those switches. And maybe part of that baseline is creating VLANs 2 through 11. Just creating them on that switch so they can be able to forward our frames in our local area network. Instead of powering up all these 20 switches, consoling into them, putting a baseline, then getting them IP, and then maybe SSHing to all 10 of them, and then putting in the VLAN commands. What we could do is just make one Python script, and then once those switches maybe have connectivity in our little like sandbox in our help desk area, we can just send this one Python script to create those VLANs. You can see here, we have this dictionary that has these key value pairs that says what type. So we're using the Cisco iOS module, the IP address, and then how are we going to SSH to it? What are their credentials? And then if we need it, then enable password, okay? So if those username and password credentials don't automatically put us into privilege mode. And then what we have here is a variable that says, hey, VLANs 1 through 10 are what we're going to create. With the 1 being obviously already created out of the box, but that's okay. And then we have this netmiko SSH session. So we're using this connect handler function to actually send commands to create those VLANs. So we see we have this for loop here that says for VLAN ID and VLANs to create this variable up here, we're saying, hey, VLAN, and then the ID looping through 1 through 10, we're going to send this command, VLAN, with the number, and then the name, and then the VLAN ID, okay? And then we're also going to save this config down here with this function net_connect.save_config. And then we're going to also print a little verification for us. So that's just one of the ways we can do scripting and orchestration in our network environment. Also with network automation, it's closely related to DevOps. So what do we mean by that? Well, typically when we work in the NOC, we'll be a part of something like IT operations. That's our role in the NOC. In a big enterprise, we may also have a development team. So DevOps bridges the gaps between IT operations and development and allows those two sections, those two teams to work together to automate tasks. So that would be our role in that. As a network engineer, we could be part of that DevOps team that's automating our network, working with actual developers on the development process. So we have cloud and SDN integration as well. So network automation also extends into our cloud environments and our software-defined networking solutions. So yes, this is when we start talking about DNA Center, our actual software-defined networking solutions that we're not scripting Python or Ansible here. We have dashboards. We have a web-based GUI that allows us to set policy and provision and get alerted about our Fabric underlay. We also get continuous monitoring and feedback with automation, so we can generate and detect anomalies, generate alerts, trigger corrective actions. So let's say for some reason we see that, we have a spanning tree loop. Well, we can trigger a corrective action that shuts down our trunks. Something like that. Now, that's a bad example. I can't think off the top of my head, but something we can't do is almost like SOAR. We have secure orchestration, automation, response. We get that with something like DNA Center. And then it also helps with our security and compliance. So we could have a situation where there's a CVE out for all Catalyst 9200 series switches running on iOS version 17.0.0.3. And now from our dashboard here, from our DNA Center dashboard, we can go throughout our whole network and bring up a dashboard that says, hey, what switches have this version? And we can make them non-compliant. And then using DNA Center, we could say, hey, to get them compliant so they're not vulnerable to CVE, let's just say 2900-1, we have to upgrade them to 17.0.0.4. And now instead of doing that the traditional way, we'd have to TFTP a new iOS into the flash and then set the boot to boot into the new flash and then reboot the device, make sure it booted into the new iOS, delete the old iOS. We could just do that all from our dashboard here in our DNA Center. Okay, now let's get into the logical planes. So before we get into logical planes, let's do a quick device overview and just go through the roles of a router and a switch. Now, of course, firewalls come into play here, access points as well, but we're just going to talk routers and switches because it's just easier that way. We've been working on routers and switchers this whole course, and still in the enterprise network, that's what we're going to be working on, especially as a new CCNA. You may just only touch switches and maybe some access points. So let's go into it. So roles of a router. So a router, at its base, why we purchase routers in the first place is because they're going to forward IP packets based off the IP header. They're layer 3 devices. Their whole role at the end of the day, if you want to break it down Barney style, is to forward IP packets, get them to their destination. We're not making sure that they not fragmented. That's part of the transmission layer, the transport layer. No, we're just forwarding off to the destination. Now, how do we do that? How do we do that reliably? And again, we're not talking TCP. How do we know where to send destination IPs without just discarding everything, right? We got to know where to send it. Well, we use routing protocols to create a global routing table and also use those routing protocols to share routing information with our neighbors. So now we're talking OSPF, technologies like ERGRP, BGP. We could also bring in like FHRP in there, first hop redundancy protocols. They also create tables and information with our neighbors to help us with routing, okay? What else does a router do? We also have management protocols like syslog, SNMP that are going to help us monitor and keep track of events on the device. So this is us sending syslog events to a syslog server, centralized server. Maybe sending them to Splunk nowadays, right? Cisco just acquired them. And then SNMP, having things like SolarWinds. Even DNA Center can use SNMP to get information from our device. So track the CPU, track interfaces. And then also, they allow protocols like Telnet and SSH to allow us to connect to the device and then manage and configure it and troubleshoot. So out of all these things here, how does this come into the logical planes? So first, let's define our logical planes. So we have the control plane, we have the data plane, and we have the management plane. I'm not going to write it all out. So out of these three planes, which ones are which? So when we're talking the actual forwarding of packets, that's actually happening at the interface level, meaning a packet comes inbound to this router and then gets switched outbound. That is the data plane. So the actual looking at the packet, getting rid of, stripping the layer 2 header, adding on a new layer 2 header, looking at the forwarding table, and then quickly being switched out this router here, that is the data plane. The data plane is that physical router switching packets or routing and sending them on the wire. Now, who informs the data plane of how to send? How do we build that FIB, that forwarding information base that says, hey, if we're destined for 192.168.10.5, switch it out via gig 01. How does it learn that information? It learns it by getting it from the RIB, the routing information base, or known as the routing table. Well, where does the routing table get its information from? A routing protocol. Routing protocols build the routing table, which informs our data plane of how to send traffic. So why is this important? Because this control plane traffic here is what we configure. That's what we go in and manage. And in traditional networks, the control and data plane sat at the individual infrastructure, which is called a distributed network. With controller-based networking, guess what we do? We take the control plane away from the individual device and put it in a centralized server, giving us a single pane of glass into the management of our devices and informing the data plane of how they send. Now, before we get ahead of ourselves, we got one more, the management plane. So the management plane, it's a little confusing when comparing it to the control plane. It still uses like a CPU for this overhead traffic, right? Not the actual switching of packets, not the actual base level job that router's supposed to do. But management plane protocols are going to be things that help us troubleshoot, that don't necessarily affect how that router or switch will forward traffic. I can enable syslog, I can enable SNMP all day, but it's not really going to affect my routing table, right? No matter what I configure for SNMP and syslog, it's not going to affect my policy-based routing or my routing at all. Telnet and SSH. I could disable these on my router. I could disable all these management protocols, and guess what? As long as OSPF is running, as long as the data plane is still working and those physical interfaces are working, packets are still going to get sent off, okay? That's management plane. Now, going over the role of a switch. It's going to be the same thing, guys. So a switch, instead of layer 3, it's layer 2. It forwards based off the Ethernet header, the source, destination, MAC address, and destination. It builds a MAC address table by examining source MAC addresses in the Ethernet header. And then it uses STP to prevent loops. It creates VLANs to segment traffic. And all this stuff, right? It's going to be the same thing. So this right here, this is also the data plane. This one is a little confusing, but the actual creation of the VLANs comes from our management plane, right? But when we're actually talking like stripping and adding an 802.1q header at the actual packet level, that's the data plane as well, okay? But it's the same thing, guys. The control plane here is STP. It's building our ARP table. All of our adjacency tables and our different tables and databases, those are going to be control plane. Okay, now, just to further talk about the data plane. The data plane is where data gets forwarded, actual forwarding, so interface to interface. This is when a packet gets de-encapsulated and re-encapsulated. That actual process of that function is done at the data plane, and that includes encapsulating like VPN headers, 802.1q headers. And then something else that may be a little confusing when talking like ACLs, discarding traffic, discarding packets due to ACLs or port security. That is also a function of the data plane. Now, of course, like us configuring that ACL via the management plane, because I SSH and I was on the CLI, that informed the data plane what to do. But that actual process of discarding packets, looking at a logical list and saying discard and getting that forwarding information base, that is the data plane. And as you can see here, incoming packet gets forwarded and switched out the outgoing interface. And that's as simple as it gets for the data plane. And this could be a router or a switch. Now the control plane. So forwarding decisions are based on the control plane protocol information. So just some examples here. Routing table, MAC address table, the ARP table, spanning tree, our OSPF link state database, or like our ERGP adjacency table. That's all control plane traffic. You can see here in our control plane, we have OSPF, we have its neighbor table, its link state database, and then that informs the routing table by taking the best routes, right? And then that informs our forwarding table. So any function or protocol that builds the tables listed above is part of the control plane. So again, the OSPF, the protocol does not actually forward traffic. It just informs the data plane by building a global routing table, and that table tells us how to forward the packets, where to send them. And now the management plane. So the reason we buy network infrastructure, the whole reason, is just to forward packets to their destination so that our users can communicate our line and our customers can reach us. This function is just the data plane, guys. That's all it is. However, the data plane could not forward accurately without the control plane, and the control plane could not be configured without the management plane. So without our management plane, we could not SSH, get into the CLI, and configure our OSPF that informs our data plane how to forward. So the management plane consists of protocols that assist in troubleshooting, monitoring, and reporting of the network device. And of course, they're needed to configure and make changes to the device. Again, we got some examples down here. The only one you hadn't seen yet is NTP. Now, NTP is needed sometimes for a control plane, but again, that's just a management thing. We could turn all these off, and we could still forward packets. Okay, now to get into the actual hardware. So how does the hardware play into these logical planes? Because when you have something logical, you have hardware in the background that's making it work. When I open up Microsoft Word, that is using my RAM and CPUs to actually do that processing. So where does this come into play? So for control plane hardware, the CPU, this is critical in the control plane's operations. It's responsible for executing control plane processes like routing protocols and also handling management tasks. So the CPU, like I said, is that overhead for that control plane and also that management plane. The RAM. This is typically where we're going to store data structures and tables required by the control plane processes. So the routing table, that's in RAM. And we know this as network engineers, that when we turn off our router, we lose that routing table. We can't save that routing table to NVRAM, to the startup config. Nope, that's running in RAM. Any adjacency tables. So our neighbor table, our adjacency table in ERGRP, that's running in RAM. And again, we turn that off, no more table. A lot of our caches, so our ARP cache, our MAC address table, okay? Or excuse me, our ARP cache. That stores the mappings between IP addresses and MAC addresses. So the control plane CPU cores. So in some modern routers and switches that require these huge management and control planes, think of like the 9400, 95, 9600 Catalyst series switches that sit in our data centers, our core, our distro switches. They're going to have those multiple CPU cores dedicated to control plane tasks. This is going to allow for multi-threading or parallel processing of control plane operations. And then also control plane hardware is going to be that flash memory, and that's used for storing the device's operating system, okay? The control plane, guess what? All those routing protocols rely on the OS for its operation and function. Now the data plane. So data plane hardware is a little different. So imagine our switch. This big beefy switch. And I'm not going to draw all 48 ports, but imagine those 48 ports doing full duplex, doing 1 gigabit a second each. And that is the expected performance we're supposed to get. A CPU cannot handle all the frames, the billions and billions of frames per second that a switch could encounter. Imagine all 48 ports here, transmitting and receiving at the same time their full gigabit speeds. That is a lot of processing power. So at the actual interface, we have ASICs. ASICs are the custom designed hardware components for optimized data plane forwarding. They can perform high-speed packet processing and switching and routing without involving the CPU. So ASICs are completely separate compute resources from the CPU and memory. So ASICs play a crucial role in achieving line rate packet forwarding in switches and routers. So there's an ASIC chip, ASIC chips for every single interface. Another thing we need to learn about is this TCAM. So the ternary, I think it's how you say it, content addressable memory. So the TCAM is used for fast table lookups in data plane forwarding. So guess what? Guess what sits at our TCAM? That's right, the MAC address table. So when we want to do those quick lookups, we use these ASIC chips to do it. And for our TCAM and our CAM table, our content addressable memory, which is also the MAC address table. So this also can be used to do route lookups, ACL matching, and quality of service classification in our switches. So this is kind of a CCNP concept, but the TCAM is where we do our QoS and our ACLs. These control plane functions, when it gets pushed down to the data plane, use the TCAM. And then, of course, we have our forwarding engines. So this is like our forwarding information base, like our Cisco Express forwarding. These are specialized forwarding engines or forwarding cards that may be present in high-performance routers and switches to offload data plane tasks from the CPU if that's what's happening, right? If we have a router or switch device using the CPU for some data plane functions. All right, so let's go ahead and move on now. We just went over our data plane hardware, control plane hardware, and the differences. Now, let's actually get into software-defined networking versus traditional networking. So now we got to define what is traditional networking before we actually go into what software-defined networking is. And I just noticed our time, we're at 30 minutes right now, guys. So I'm going to go ahead and stop this video and see us for part 2 when we get into software-defined networking, southbound and northbound APIs.